Okay. Yeah. Okay. Cool. So let's get started. Let's see. Okay, yeah. Right, so today we are going to be discussing the second set of questions. There's a lot of overlap between the first set and the second set, but there's also some new concepts. So if you have any questions about any of the concepts, we can totally focus on that. Else, I'm going to talk about what I think is most relevant. That sound good? Okay, cool. Let's see. I want to okay, cool. So today I hope to discuss two main questions. One is, okay, so the first is sketch a potential energy interatomic separation curve representing the following factors. Wait, where was it? Yeah, sketch and label the energy distance curve for the following metals exhibiting high elastic modulus, low hardness, high self-diffusivity, and low melting point. Explain your answers briefly. And then the second thing I want to talk about is briefly describe 4 ways to strengthen a metal. Give diagrams to illustrate your answer. Okay, so to begin, I think we should discuss what is the energy versus atomic distance graph. We talked about it earlier, but we can reintroduce it again. So it looks something like this. And on the x-axis here, we have R, which is the space between two atoms. And on the y-axis here, we have energy. So if the atoms, so atom 1 is going to be at position 0, right? So this is atom 1. And then we're going to place a second atom somewhere here in this direction. And if it's really far away, like all the way over here, the atoms can't interact with each other. They're too far away to interact with each other, right? It's not, the energy is 0, right? But if the atom is super close, then they're too close to each other. They're trying to occupy the same site. And there's a lot, they don't like that at all. That's not, you're trying to force two atoms into one site. That's not going to happen. So if they're too close, then the energy is really high. And so what happens when we're in this region in between? Well, we end up with a curve that looks something like this. So if the atoms are too close, the energy is really high because they're repelling each other. If the atoms are too far away, the energy is 0 because there's no interaction. But here, we see we have a local minimum, like this point here. And so at this point, the atom is close enough to, the atoms are close enough that there's an attractive force keeping them together, but they'll fall enough away that they're not stepping on each other's toes, so to speak. And what happens is we get a bond, right? So this R naught value is equivalent to the bond length. And this is one way we can model a bond, right? So this is one way we use to model atomic bonds. And it is pretty, in some regards, it's pretty elementary, but in other regards, it's very elegant. You know, it's really a simple way to really get the point across. So the things we have, this is a graph we're going to be manipulating, and the things we have to show is we have to show Young's modulus, hardness, melting point, and self-diffusivity. Okay. So the first thing I think we should talk about actually is melting point, right? And so this graph assumes that we're talking about chemical bonds, but more importantly, chemical bonds in a solid material. Like, so we're talking about in a metal, right? Where each atom has its specific lattice site, and it will. Can you repeat what you wrote for number? Yeah, cool. So we're going to use this graph to discuss materials that have different properties, and the 4 properties we will be discussing are Young's modulus, hardness, melting point, and self-diffusivity. So this is actually on the second set of homework questions. This is question 4. Okay, cool. So yeah, so as I was saying, we're going to start with melting point. Melting point is the first material property we're going to discuss. So as I said, this model describes, you know, atoms in a solid, right? So one atom has its lattice point and it stays there, and another atom has its lattice point and it stays over there, right? And so solids are ordered, right? Solids are very like ordered, boop, 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 boop. But like liquids are not ordered, right? Liquids are random, right? There's still interactions between the atoms, but it's very loose. It's very like, oh yeah, you know, go wherever you want, right? So really what we're saying is that when we go from a solid to a liquid, we're breaking all of the bonds in the solid. That's really what we're saying. When we melt iron to make a, you know, a melt, like we're breaking all the bonds in the iron, right? So what in this graph describes breaking all of the bonds, right? So this is the bond length. So these 2 atoms are bonded, right? Are these 2 atoms bonded together? No, these 2 atoms aren't bonded together because they're so far away, they don't interact with each other. So functionally, the melting temperature, or the energy required for melting, rather, is related to the energy required to break all of the bonds. So it's related for the energy required to climb this hill and break all the bonds. So this magnitude is related to the energy required to melt all of the bonds. It's proportional, right? So we have this one material A, right? And now I'm going to draw a second material that has the same bond length. It has the same bond length, right? But now it has a profile that looks like this, right? And B, we have the B in black here, right? So they have the same bond length. So that means they might be similar in a lot of ways. But now B has a much lower, a much lower local minimum here. So now more energy is required to bring the atoms away from each other and break the bonds. So what we can say is that B has a higher melting point than A. Because a melting point is a function of temperature, right? Is a function of energy. So the higher the melting point, the stronger the bonds. And that's what we're saying with B. Good? Cool. So now we can apply this similar logic to the other mechanical properties that we know. So the next one, I guess we could talk about is self-diffusivity, right? And so self-diffusivity is kind of, this is the one that I always have to like stop and think about. But what it's saying is, atoms diffuse through a material, through a specimen, right? And oftentimes they diffuse through vacancy diffusion, where you have an atom and I'm here and I'm a little upset. There's an open spot here. I'm going to jump to this spot, and now I am in a different location. And then I might jump back, and then I might jump down, and I might jump, right? And so every time you do that, the atom has to break its local bonds, move to a position, and form new bonds, right? So if we look back at these two materials we have, right? Self-diffusivity is saying atoms have to break bonds, the current bonds they have, move to a new position and form new bonds. So in this case, the atom has to break all of its bonds and form new bonds. Oh, and in B, it has to break all of its bonds and form new bonds, again at this new position. So it's easier to break the bonds in A because the bonds have less energy, right? It's easier for atoms to diffuse through material A because each time they jump, they have to have less energy. So this force relationship says that for melting point, B has a higher melting point than A, right? But for self-diffusivity, A has a higher self-diffusivity than B. So melting point and self-diffusivity are inversely related. That's how we would describe them. And so this graph kind of just is a way that we can really describe materials in a very interesting way. So melting point and self-diffusivity have to do with their intrinsic properties to your sample. And another intrinsic property we have is Young's modulus, right? So Young's modulus is the stress-strain response of a bond in the elastic region. And so what I mean by that is that you have two atoms bonded in space. If you stretch them a little bit, right, they will stretch and then they will relax when you stop stretching them, right? So we're not breaking bonds. We're just stretching bonds. And so we will discuss this again in more detail in a minute, but because we're just stretching bonds a little bit, we're just elongating the bonds slightly. So if we return back to this graph, we can say that if this R0 is our bond length, what happens when we slightly stretch the bonds? Right, when we slightly stretch the bonds, we're looking at this region here, this domain here. So there's this slope. And it's basically saying to get this much elongation, we need this much energy in. And then for material B, we have a second slope. Like this, right? And so for material B, the slope is higher, right? We need more energy. We need more energy to elongate the bonds. So what we can say is for Young's modulus, which we describe as, we write as an E, right? For Young's modulus, B has a higher Young's modulus than A. Because looking at this graph, the region directly to the right of the equilibrium distance, the slope is higher for B. So more energy is required to elongate the bonds. And now the last mechanical property we have to talk about is hardness, right? Hardness is like the opposite of Young's modulus. So while Young's modulus, we stretch the bonds, and hardness, we compress the bonds, right? We're compressing the bonds. So hardness really is a resistance to compression. And so in that case, we're looking at the slope of the curve on the left side of the equilibrium point, right? As we try to bring the atoms closer together. So this slope versus this slope. And again, we can say that B is a harder material because more energy is required to compress the atoms together, right? So for hardness, we'll just make that an H, and we'll say B is harder than A. How does everyone feel about that? Yes? No? Should I repeat something? Good? Okay, cool. Thank you. This graph, I think that this graph is very interesting. And I know that Dr. Clayton also thinks this graph is very interesting. So I hope everyone else can gain an appreciation for this type of graph. Okay? Can you repeat hardness? Yeah, of course. So Young's modulus or tensile, like Young's modulus describes tensile strength. So when we stretch the bonds, right? We're stretching the bonds. Hardness, let me just make sure I get this right. Yeah, okay. Yeah. So hardness describes a response to a compressive force, right? So while Young's modulus is a tensile elongation, hardness is a compression, right? You know, because like rocks are hard because they're hard, and like a cake is soft because you can squish it, right? And so in that regard, we're looking at the area to the left of the equilibrium distance, right? Because if this is the equilibrium distance, now we're bringing the two atoms closer together. We're compressing them. We're seeing the response to compression. So in that regard, we're really interested in the amount of energy it takes to do so, right? So to move the bond this distance, right? To move the bond from here to here, we require this much energy. For material B, to move the material the same distance, we require that much energy, right? So more energy is required to compress the bonds for B than for A. So we can say that B is harder than A. Cool. Great. So that is a really interesting concept, I feel, and I hope everyone else can gain an appreciation for it. The next thing we're going to talk about, briefly describe 4 ways to strengthen a metal. Give diagrams to illustrate your answer. So I am going to, okay, so because we started late, I'm willing to go 15 minutes later than 9:30. If you're busy, this lecture is recorded, so I will post it as well. So don't feel bad if you have to leave. And I will start by listing the 4 methods, and then we will go through each of them. How about that? Cool. So the next topic we're going to be discussing are the 4 methods that we can employ to strengthen a material, right? So oftentimes we have a material that we engineer for one property, but it's weak in another property, and so like this happens a lot with steel. People engineer steels to meet different, design specifications, or I don't know. I'm not a metallurgist, so but people do this a lot, and it's and one of the few things as material scientists that we can control is the chemical composition. So that's like what we mix together, right? What atoms we use, and then also the time in which we mix them and the temperature at which we mix them. So those are the 3 knobs we can, really manipulate. And with that, we can make a lot of really interesting, cool material science. So let me list out the 4 ways, and then we can discuss them more in depth. Okay, so the first method, we have cold walking or strain hardening, right? So cold walking, strain hardening. Then we have grain size control. Number 3 is solid solution strengthening. And number 4 is precipitation hardening. So this is trash. These are a mix of processing techniques and post-processing techniques that affect different length scales of the material. So, for example, solid solution strengthening, right? This is a processing technique where we don't. Morning, Allie. Good morning. Solid solution strengthening is a processing technique, right? So this is done when we're making the material. Same with precipitation hardening. However, grain size control can be done during processing or post-processing. So after we initially make the material, or maybe not. And code walking is done after we've made the material. Yeah, I will use the blue pen. Yeah, that other pen is died. So yeah, I will. Thank you. So let's start with code walking, because that's like, to me, I think that's the best one. So let's do that one first. Oh yeah, this is okay, thank you, Tyler. This is much better. Okay, so here we have a graph, and this is a stress strain graph, right? So we discussed this last week. This is what's gonna happen is we're gonna take our material, we're gonna pull on it, and then eventually it's gonna break. But first, as we apply a stress, we're gonna measure a strain. And at first, that's gonna be linear, right? We're just stretching the bonds, we're not breaking the bonds. It's a linear behavior. And then eventually, atoms will start to move, bonds will break, and atoms will reform, right? So, and then we will get some plastic deformation that will occur. And eventually our material will break, right? So we have the elastic linear region and the plastic region here, right? And we described how during plastic deformation, dislocations are moving, right? So as atoms move, they break bonds and make new bonds, and that results in dislocations moving across grains and across the crystal as a whole. So additionally, the elastic region is reversible, right? So I can stretch to this position and then the material will relax to its initial position. However, as soon as I start inducing plastic strain, plastic deformation, I'm permanently deforming the structure by moving these dislocations. And as a result,
hey, I was wondering if you could come in for a couple minutes.
And as a result of that, right, so I'm introducing plastic deformation here, and then I got to this point, say I get here. And now I'm like tired because I was like pulling on this metal rod for like an hour. It's like I'm tired. And then I go to eat. I go to eat lunch. And so the material relaxes. But it doesn't go back to zero, right? It goes to this new point here. And I've introduced a permanent strain into the material, right? Now the material is permanently deformed, right? So then I'm like, I call my buddy and I'm like, hey, I'm not going to make it back to the lab. Can you finish this experiment for me? Like, I'm not going to be there anymore. I'm tired. And so then they go back to the lab and they do the same experiment where they start pulling on the material. However, they don't know, right? To them, this is now the material response, right? So the material response, now this is the elastic region and this is the plastic region. Whereas before, it looked like this, right? And what we end up happening is that the yield point now is much higher after we introduce plastic deformation, right? So as a result of plastic deformation, our yield point is higher. So our material is now stronger, right? So, and when our material is stronger, it is better, right? And that's what we were trying to do. We were trying to strengthen our material. And then we can continue to introduce a little bit more plastic deformation. Right? And now we've introduced even more strain. And we can continue to do this as long as we have more room on the plastic deformation curve. But eventually we'll get to this point here where we've strained the material too much, right? And now if we continue to strain, our yield point actually decreases, right? So that's kind of bad because now we're closer to breaking. And every time we introduce plastic deformation in this way, we're making our remaining plastic deformation smaller. And oftentimes, plastic deformation is a visual indicator that, hey, something's breaking. Like, you know, like if we're seeing plastic deformation visually, it's like, oh shit, something's going to happen to our bridge. So we can't do strain hardening so extreme that we end up at this point, right? Like, because yeah, we have a strong material, but now we have a very small plastic region to work with. Nevertheless, this is done a lot to like strengthen materials about 10%. And I think the most common thing is like, I don't know, like blacksmithing. I don't know, that's the example they use in the book a lot. Like, oh, when the blacksmith is hammering a sword, but I don't know, I've never. That's the example they use, but it's also used for a lot of other things. And it's called strain hardening, or it's also called cold walking because it's done at cold temperatures. And when I say cold temperatures, I mean cold for a metal, right? If the metal's melting point is 2000 degrees, then 300 degrees is cold, right? So that's. Any questions about strain hardening? No? Okay, cool. Cool. The next method we have is grain boundary, grain size control. So as we described earlier, right? Like, so when we introduce plastic deformation, we force the dislocations to move, right? We're forcing dislocations by introducing a stress or a strain to move. And then by doing so, the dislocations will move from their position to the edge of the grain that they occupy. And in that way, we've introduced plastic deformation or plastic strain, right? So this is our dislocation. Dislocations are denoted by upside down T's. And then we tell that we introduce a force and the dislocation moves across our sample. Now, grains in a material are just regions of order. So In this region, the crystal's oriented in this direction. Maybe over here, the crystal's oriented in this direction. It's still the same crystal system, but they're two different crystals, right? And these grains can range from being very small, you have sub-micron size grains, all the way to huge grains that you can see visually with your eye. So if you look on like a size of steel, it looks spotted, right? Those are the different grains that we can visually see in the steel, right? So those are regions where the atoms are oriented in one range or the other. And so this is, in this case, we have a dislocation move from one side of the material to the other side. Right? And when it did that, it disrupted this whole region, right? It disrupted this whole region as it transfers through. It disrupted all of those atoms. Now, what would happen if we had a grain boundary here? Now we have two grains, and this dislocation now is going to move through the material. So it moves, and then it meets the grain boundary, and then it stops. Right. So now before when this was one grain, it traversed the whole material. Now that there's two grains present, the dislocation only traverses half the material and does not go into the new grain, right? So the dislocation is isolated to the grain that it's in, right? So now this material is undisturbed by this dislocation. This material remains pristine. And in that way, we can say that, okay, so now this material is not undergoing plastic deformation the way that this one is. So now more energy is going to be required to induce plastic deformation in this region, especially if this is the only dislocation present. So what we can say as the grain size decreases, the yield stress increases, right? And the yield stress is the point at which plastic deformation occurs. And now because the grain size is smaller, and this region we had didn't undergo plastic deformation, now more energy is needed to induce plastic deformation. So I'll just draw it out again. So this is kind of like the material divide, the diffusion, the dislocation going through the whole grain on this side, and the dislocation being stopped by a grain boundary on this side. And this can be modeled experimentally. As the yield stress is equal to some initial yield, some initial stress value plus K times D to the 1/2, and D is the grain size. So sigma naught and K are constants for each material. So what you would do is you would make a bunch of samples with different grain sizes, and then you would break them all. You would do tensile tests and break them all, plot the data, and if you plot yield stress with respect to grain size, you will get a power relationship, right? And from that graph, you can derive your two constants. And that becomes really powerful because then you can use this relationship to predict tensile strength of materials based on grain size. Okay. Okay. The third one we're going to talk about is precipitation hardening. Okay, so this is our sample. You can see we have different grains, right? And now, so during precipitation hardening, what we're going to do is we're going to induce the formation of a second phase. And that second phase will have a property that we are interested in. So for example, you know, aluminum, right? Aluminum is great. It's like lightweight and cheap, and it conducts electricity pretty okay. Like it's a very good material for a lot of things, but aluminum's also very, you know, it's also very weak. You know, it's very easy to physically deform. So if you're making an aluminum alloy, that's a big problem you have, is that your material becomes weak. So what you can do is during processing, like instead of having 100% aluminum, you might have, you know, 95% aluminum and 5% some other material. And so you make your alloy, you cast it, it's cool, and you have this polycrystalline aluminum material. And when you heat it up for a long time, you heat it up, you put it in the oven at an elevated temperature, the 5% impurities that you added, they will start to diffuse, and they might meet up at the grain boundaries, you know, because atoms will diffuse to the grain boundary naturally. And then they might say, oh, hey, okay, bye, Jacob. You're an atom, I'm an atom. We want to make our own crystal structure, and we will do so. And so then what will happen is we will form this second phase at the grain boundary. Okay, so at the grain boundary, we will form the second phase. And if the phase is stronger, like if these second phases, they just all have higher mechanical properties, then your overall specimen strength will increase. And so that's all we're saying here, is for precipitation hardening, we're precipitating out a second phase that has our desired property. It could be hardness, it could be electronic conductivity, it could be tensile strength, but we're forming that in our crystal system, and we're getting beneficial use from it. So now when we apply a stress to this material, it is harder to deform because these secondary phases are stronger. Cool. the last one is solid solution strengthening. And let me see if I can go get another marker real quick. I'll be right back. Okay, I guess we're just gonna have to do. Thank you. You're the best. Thank you. Cool. All right. Oh my God, that's horrible. Hold on. Okay. This is our crystal structure we have here. And I hope everyone can identify the edge dislocation. So the edge dislocation is the extra half plane of atoms we have. Right here, right? So upside down T signifies the edge dislocation we have. And right above the edge dislocation, we have 3 atoms trying to reside in the positions of 2 atoms, right? So we have 3 atoms trying to reside in the position of 2 atoms, right? So they are in compressive force, compression, right? Because you're squeezing the 3 atoms in the site of 2 atoms. And now below the edge dislocation, now we have 2 atoms that are being stretched to bond to the 3 atoms above it, right? So then these are intensile, right? So those are intensile forces, right? Because they're being pulled apart. Okay, so now bear with me for a second as we go up here. Okay, so now keep this in your mind, think about this for a second. And now if we go up here and we say, this is our atom, these are our atoms. What happens when we put a larger atom inside, right? So we're gonna dope our material with a really big atom. this atom's really big, it will push on all the surrounding atoms, right? So it will push and introduce compressive forces. Compression, right? And if we look on this side, now what happens if we introduce a very small atom, right? Now it will induce a tensile force, right? It will introduce a tensile force because it's small and it pulls other atoms close to it to bond. So big atoms introduce a compressive force. Small atoms introduce a tensile force. Okay? So now we have these two things going on. We have dopant atoms of different sizes introducing forces, right? And we have these dislocations that are defects in our material that are also introducing compression and tensile forces. And so just like how I like to think of it as how, how opposites attract, positive and negative charges attract each other. Opposite forces also tend to attract each other. So if we have a small atom up here, right, that wants to reside in the crystal, but in order to do so, it will introduce a tensile force. It will diffuse or be attracted to regions of compressive forces, right? So what would happen if we replace these three atoms above the dislocation with three little guys? Right? So now we have a region of compressive stress, and the atoms that are smaller are relieving that compressive stress. Likewise, below the dislocation, we would have the big atoms diffuse. So now the big atoms that want to reside in regions that introduce compression, they will reside in regions of tension. And by just trying to lower the energy states, atoms will naturally diffuse to these regions. And so what happens is dopant atoms, dopant ions, alleviate the stresses introduced by edge dislocations, right? So, and also it makes sense if you think about it, like above the edge dislocation, you have three atoms trying to squeeze into the size of two atoms. So if you make the atoms smaller, they will squeeze into that size easier. And now below that, you have two atoms being stretched. So if you make the atoms bigger, then the atoms can easily stretch into those two sites to bond to the three atoms above it. So yeah, so solid solution hardening or strengthening, I think is the most complex and unintuitive of the four methods. So if you understand this method, I think you're doing a good job. And I think everyone is doing a great job. So if you have any questions, obviously always feel free to email me. This lecture is recorded and I will post it so that you can review it at your leisure. And I hope everyone has a great day. And thank you for pushing back the time a little bit. That was very helpful for me. So I appreciate that a lot. So, okay, have a great week. Okay, bye-bye.